we don't always have to multiply by the full denominator. What do I mean by that? Well, let's look at an example with fractions. Let's say we have this, which I could also just have written as 1/12 plus 1/18. So sure, in this case I can take the whole denominator and the whole denominator and use it as a trick to multiply by 1 and multiply by 1. That's going to get kind of big. I mean, 12 times 18, maybe that's pretty simple. Maybe it's a large number and it's kind of scary. I can do things a little simpler if I just look at 12 as 2 times 2 times 3. And what I want to do is I want to find the least common denominator. So I can just multiply this by 3 and this by 2. I can't just do it to the denominator. I have to do it to the numerator as well, using my trick, multiplying by 1. But that would work out just fine. And in this case, I just get 9 times 4, which is 36. So 3 over 36 plus 2 over 36 gives me 5 over 36. Okay. Well, the same is true when we have, say, an expression like this. Let's say I want to add this to this. Let's just make this an x in the top. Okay. And we're told that x is not 0 and x is not 1. Well, I could multiply both the top and the bottom by this whole denominator, x squared times x minus 1. That's a lot of x's. I'm going to have polynomial degree 6 down here. That's pretty big. So I don't want that. I can do things a little simpler by just multiplying this by x and this by x minus 1. Of course, I can't just multiply the denominator. I have to multiply by 1. But I also know that x is not 0, so this is not 0 over 0, this is 1. And since x is not 1, this is actually 1 as well. It's not 0 over 0. So now we have a common denominator. So what do I have? I have this. And that's going to be added to this. So instead of finding a common denominator by just multiplying the whole denominator of one term to the other and vice versa, we found the least common denominator, the minimal amount that we needed in order to find the common denominator, just like we would do with fractions like we did right here. Well, we're not done. We have to do this last step. I'm going to multiply this out. X cubed minus x squared plus x squared minus x. I could have waited till later to do that. It's completely up to you. That actually is going to cancel out nicely because this and that canceled out. So I get this in the top plus this here over this. And I can even factor out an x. Which I can then cancel. What did I do? I have x times x down here and x over here, so I'm dividing the top and the bottom by x, or I'm multiplying the top and the bottom by 1 over x. Since I had 2 x's here, I now have 1x. X times x is now just x. So that gives me, in the bottom, x times x minus 1 squared, and in the top, x squared. I'm going to write this x first, just to have my polynomial in descending degree. That would be x to the 1. That would be the constant term. And now I'm done. I'm not going to be able to get an x minus 1 or an x out of that numerator. So I have simplified, and I have added, and I've done it without multiplying by a ridiculous denominator. If I had done it by multiplying by all of this to the right and all of this to the left, I would have gotten something very complicated here. Maybe something I couldn't factor, maybe something I couldn't simplify quite as far. What I would have gotten would still technically be correct if I didn't need to simplify it all. But many times we do. Many times we're going to be wanting to set our rational expression equal to some value. And in that situation, if you have a degree 6 polynomial, that's going to be really, really difficult. But in this form, maybe not so much. In any case, that's a nice example of a few things. So you don't always have to go for the whole denominator. You can just sort of find a least common denominator when it comes to rational expressions.